Well, we're nearly done with the topic of relations. Just want to do a little bit more on a particular example of equivalence classes. An important example of equivalence classes, namely the integers modulo n. So, integers modulo n. Now, the equivalence relation, congruent modulo n, partitions the set of all integers into n equivalence classes. We can represent them by equivalence classes 0, 1, 2, and so forth, up to n minus 1. Now, these equivalence classes are called the integers modulo n, or integers mod n, and they have nice arithmetic properties which we summarize in this theorem here. Namely, if we let n be some natural number, and let a and b be numbers between 0 and n minus 1, then if we pluck out some number from the equivalence class of a, so that is x is some number that's congruent to a modulo n, pluck out y from the equivalence class of b, so y is congruent to b modulo n, then the sum of x plus y is in the equivalence class of a plus b. And the product of x and y lies in the equivalence class of the product of a and b. So when we do this sum, we can almost just do the sum of two smaller numbers that lie in here. When we do this product, even if x and y are very, very big, well, it has to lie in the product of two quite small numbers. This is quite a handy little property. So let's do some scratch work to prove this. I want to prove that if x is in a, y is in b, then x plus y is in here, and x times y is in there. So there's just a little bit of arithmetic to prove this. Well, since x is in the equivalence class of a, and y is in the equivalence class of b, we know that n divides x minus a, and n divides y minus b. So we can turn this around to write x as a plus some multiple of n, and y is b plus some multiple of n. And then the rest is just arithmetic. So, in particular, if my mouse works here, this means that x plus y is a plus b plus a multiple of n. X times y is a plus b plus a multiple of n. And of course, this is an integer, and all of that stuff is integer. This immediately gives us that n divides x plus y minus a plus b, and n divides x times y minus a times b. And this is exactly what we need to prove that they're congruent to each other. And so our proof runs very, very similarly. So let n, a, b, x, and y be as stated. It's just a little bit of a shortcut for us, so we don't have to say let a, da, 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 da. We can just say, hey, look at the theorem. Okay, so let them be as stated. Then since x is in here, y is in here, we know this, and we know this for some k and l in z. Okay, so this is just restating what we just did in the scratch work. It's really not very different. From this, we have that x plus y is a plus b plus a multiple of n. xy is a times b plus a multiple of n. And so, n divides x plus y minus a plus b. N also divides x times y minus a times b. And so, this is enough to show that x plus y is congruent to a plus b, and so it sits inside that equivalence class. And x times y is congruent to a times b, and so sits inside that equivalence class, just as we were needed. Okay. So this gives rise to what we call modular arithmetic. So the results of that theorem tell us that we can do some nice tricks with those equivalence classes. So again, let's take a natural number and look at the equivalence classes congruence modulo n. Then the integers modulo n is the set of these equivalence classes. Okay, so we're kind of tweaking what we mean by integer here. We're sort of expanding it, working from it, to call the integers modulo n to be this set of equivalence classes. And the previous result tells us that we can kind of treat these equivalence classes like numbers. In particular, the elements here, the integers modulo n, can be added and multiplied. They can be added by this rule, that a plus b is a plus b. So that is, if we take something, one equivalence class and another equivalence class, we can extend addition like this. And if we take one equivalence class and another equivalence class, we can extend multiplication like this. And this is a handy little trick. It tells us that any element of this equivalence class and any element of this equivalence class, when we add them together, lies in this equivalence class. We take any element of this equivalence class and this equivalence class, multiply them together, they must lie in that equivalence class. This is a handy trick for doing things like checking your arithmetic operations. It also gives rise to all sorts of interesting mathematics, which you don't have time to do in this course, but no doubt you might come across in a future course that you study. Let's stop there.